Hey everybody, today we are going to talk about evidence for the Big Bang Theory. We talked about some observations that help us to understand and see that the universe is expanding, right? We said galaxies are moving away from us and they are moving faster the farther away they are. That tells us the universe is expanding. But we have this theory that it all started with this Big Bang, this everywhere stretch. So I want to explore just what is some of the evidence for the Big Bang Theory. Because in science we have to have theory plus observations to really have anything that makes sense. So the evidence we're going to look at today is called the cosmic microwave background. This can also have other names. It can be called the cosmic background radiation, various other forms similar to that. We are going to call it the cosmic microwave background, or the CMB for short. It is cosmic because it's everywhere in the universe. It's microwave because that's the wavelength that we see it. And it is background because it's in the background everywhere. So let's get started here. If all the matter in the universe was in a small volume, that's what the Big Bang Theory says. Okay, so if that is true, right, we saw in our lecture tutorial that it's got to be hot, right? It was very, very hot. And what do hot things do? Hot things radiate energy, heat, and light. By the way, this picture here is a picture of the cosmic microwave background. I'll show you some more of those later. So, everything was in a small volume, had to have been very hot. That's what the Big Bang Theory tells us. So, could we possibly see the light, that radiation coming from the Big Bang? That's the idea. Okay. When were we able to see the very first light in the universe? Well, the first light, the very first photons, remember we have this idea of energy and matter, and first we had just energy and then it started becoming matter. This is all tied into this idea of first light. First light, the first photons, escape. And what I mean by escape is that they become visible. They're no longer part of this tiny little blob of energy that is the universe, right? The universe expands, matter forms, and light becomes this separate thing that we can see. This happens when matter undergoes something that we call recombination, which is a bit of a strange term because it's really just combination in a way. It is when electrons and protons get together to make the first atoms, hydrogen atoms. So when electrons and protons become hydrogen atoms, they combine. So when we have matter, the very first atoms in the universe, this happened about 300,000 years into the universe. It sounds like a long time, but not so much when you're thinking 13 billion. At this point, the universe had cooled, and the temperature of the universe was about a few thousand degrees. Oops, thousand Kelvin. Like the sun's surface, a few thousand degrees. Again, hot, but nothing like it was in that moment of the Big Bang. Okay, so take a look at this picture. We need to think about this idea of escaping. So in the top half here, the purple arrows are the photons, the light. The red and the blue are protons and electrons. And they weren't together, they weren't atoms yet. And so what was happening, those photons got bounced around. Remember inside the sun? Remember the beach ball that we did in class? The photons get bounced around. They can't get out. They can't escape. It's like a fog. The light gets scattered in that mist or in that fog. But when those atoms get together, the protons and the electrons get together, the fog clears. Light has a path. It escapes, so to speak. This is the first light that was really allowed to go anywhere in this newly expanding universe. First light, okay? So, the cosmic background radiation, the CMB, is this first light, but we're seeing it billions of years later. And we have to remind ourselves that in those billions of years, what's the universe been doing? It's expanding, due to expansion. Due to the expansion of the universe since that time of first light. That first light, got cosmologically redshifted. So first light was redshifted. We talked about cosmological redshift, which is redshift that happens when light gets stretched. Look, here's the picture. It was blue and close together. Space stretched. It stretched out and got redder. All during this time of expansion, too, the temperature of the universe is dropping. Temperature of the universe decreases. It drops. So how is this related? How is it relevant? Okay, so here's the stretching in this picture. Look at the graph. The graph is showing us temperature. Really high at the beginning of the universe, really low now. Because as you expand, you're putting that matter and energy over a bigger space. It's getting cooler, right? Heat wants to expand. So, turns out, remember color and temperature are related? Blue means hot, Wien's law. Blue light becomes red light. Temperature drops. So, we put it all together and we say that the cosmic microwave background is really that first light, which when it first came out was probably visible light. The temperature was right, like the surface of the sun. Has now been redshifted to the microwaves. That first light from the early universe at recombination is now microwave light. Okay? Is now microwaves. It has been shifted all the way in to the almost radio, from visible through infrared into microwaves. After the Big Bang Theory first came out, this was predicted by these gentlemen, sort of, that you see here. So let me tell you the story. This is one of the great science stories. It was predicted by these guys, Alpha, Betha, and Gamow. Okay, here they are. Alpha, Betha, and Gamow. Okay, actually, Betha, the guy in the middle, beep, he did not have anything to do with this. It was really Alpha was Gamow's student. But Gamow, he was kind of a bit of a jokester. And so when they wrote this paper and predicted that the current temperature of the universe, this is what they predicted, the current temperature should be very low. It should be 5 to 10 degrees Kelvin. That's almost absolute zero, very, very cold. So they wrote this paper in 1948 and they predicted this would give us microwave radiation. This guy, Gamow, said, hey, this paper would be a lot cooler if we could call it Alpha, Beta, Gamow, because it's like the Greek letters, see down here, Alpha, Beta, gamma. Those are the first 3 letters of the Greek alphabet. So Alfred Betha Gamov, Betha was just kind of thrown in there for fun. He is a scientist, but he wasn't really part of the story. So they predicted it in 1948. But we could not see it. We did not really have the tools to see it at that point. It was just a prediction. Then in 1965, these guys came along. This is Penzias and Wilson. I like telling the history of some of these science stories because science isn't always linear. Come on, pen, work for me. In 1965, these guys, another great story, found the cosmic microwave background, the CMB. Here are their names, by Penzias, good name, and Wilson. And they used that big radio telescope that you see behind them. It looks like a huge ear trumpet or something. But they were not looking for it. So it was found by Penzias and Wilson with a radio telescope. And they found it at a temperature a little bit lower than what Alfred and Gamov had predicted, at a temperature of about 3 degrees Kelvin. Okay, so back to Penzias and Wilson here for a minute. They were looking for Russian satellites. Okay, this was the space race. They were trying to beat the Russians. They wanted a way to communicate with satellites and listen for satellites, built this big radio telescope, but it always had a static in the background. Could not get rid of the static. Talked to some friends. A guy at Princeton said, "Hey guys, what's the temperature of that static?" "Oh, about 3 Kelvin. "Oh, by the way, have you read that Alpha Beta Gamma paper?" "Yeah, that static that you're seeing is the cosmic microwave background." Awesome. They share the Nobel Prize for that discovery, even though they weren't even looking for it. So cool. Today, we have come a long way. We've sent satellites into space to get a better picture of this. Here's what Penzias and Wilson saw, green blob, right? We've been able to refine this over the years with a number of satellites. The red in the middle is our Milky Way galaxy. But what we see are all of these bumps and wiggles. These are tiny temperature variations. And I just want to end with this. A little bit of science for y'all. The Big Bang Theory predicts a temperature curve that looks like this. When you look at different wavelengths in the microwave, you see how much energy there should be, and the red curve is what is predicted. With our most modern satellites, what we do is we take temperature measurements of the universe all over the sky. Those are the black dots. The black dots fit the prediction beautifully, and our current temperature is a little less than Penzias and Wilson saw, about 2.7 Kelvin. So the universe has cooled over 13.5 billion years from super, super hot to just above 0. Awesome discoveries, awesome work, awesome science. See y'all next time.